Okay, thank you so much. First of all, I would like to thank the organizers for coming up with this great idea and turning this into a virtual reality. I think it's great, and I hope that it will continue for many years. And also, I would like to thank you for inviting me to participate in this event. And today I'm going to talk about peridynamics-enabled learning partial differential equations. And all the credit in this presentation really goes to my PhD student, Alican Bekar. And here's the outline of my talk. Basically, I will describe what learning partial differential equations are, give you a very brief background, and describe the approach that we've taken in this study, and also describe what learning algorithm is and show you some numerical results concerning some challenging partial differential equations and make some few remarks. So learning partial differential equations is an approach really to discover the significant terms in partial differential equations to describe a particular phenomena based on the measured data. And usually the measured data has some noise. Okay, here, for example, you see this partial differential equation here, and the boundary conditions, in this case, it's subjected to periodic boundary conditions. This, what you see on the right-hand side, is the given data. We have initial conditions. So what we want to do is determine the differential operator L here, okay? So this notion of learning partial differential equations was introduced by Schaefer in 2017. So a very brief background on this. You'll see the first work or related to this, relevant to this work is Baumgart and Lipson, 2007. They used genetic algorithm to generate the best linear and nonlinear functions for constructing the candidate space, and they derived the governing equation of a dynamical system. In 2016, Brunton and his colleagues used a library of numerically calculated derivatives and polynomials of the field variables as possible candidate solutions, and were able to derive the governing equation of a nonlinear coupled dynamical system. And Schaefer and his colleagues, 2013, included a few solution modes along with a sparse regression algorithm, and were able to discover solutions of multi-scale PDEs. Then Rudy and his colleagues, 2007, they used the macroscopic behavior of the field, and by examining the microscopic behavior, which is a Brownian motion, and they were able to come up with the governing differential equation of this field equation. However, in their case, they failed to recover, for example, the coefficients of the Kuramoto-Sivashinsky equation properly. And 2017, Schaefer used the spectral method for spatial derivatives, and also used Douglas-Rachford algorithm for sparse optimization, and introduced the concept of learning partial differential equations. Spectral method may fail depending on if you have a discontinuity to capture the underlying dynamics. So the approach here is, as I mentioned before, introduced by Schaefer. So what we do is, given the data set here, we construct a candidate space. And in this candidate space, we have a feature matrix, which has the possible candidates or derivatives that you may have in the partial differential equation. So the field variable itself is squared, the first derivative, the square of the first derivative, the second derivative, and so forth, different combinations of. So you construct the feature matrix, and you have a velocity vector, and then you have the coefficient vector that you need to determine. These are the coefficients that you have in your partial differential equation. So basically, we set this up as a linear least square minimization problem to determine the coefficient vector, and that's the least square minimization. Here we have a parameter lambda. This is a regularization parameter. You have an L1 norm here, and lambda is always positive. So if you were to go through this minimization procedure, you're going to end up with a system of algebraic equations. It's a regression problem with an overfitting. So what we do is we set this up as an optimization problem with a sparse solution. And for that, we use Douglas-Rachford algorithm. And it's an iterative scheme. It uses proximal operators. And here you see the proximal operator here on the functional h. It's always convex because it has a least squares construct. So it has a unique minimizer and always has a minimum. So the convergence rate is 1 over n, even in the worst case scenario. Okay, so this is our least square minimization, and we define our function as h1 as lambda alpha, it's the L1 norm, and we have h2, and we apply the proximal operators on these. And as described in this reference here, we set this up as a two-step iterative scheme to determine alpha. So in here you see a gamma, and here you see a mu, and these are basically hyperparameters that come with the scheme here. And lambda is another constant, it's a regularization parameter, but we determine that based on the parsimony interval. So we construct the feature matrix by using the peridynamic differential operator because we need the spatial derivatives, okay? So what it does for us is it allows us to obtain differentiation of nth order in m dimensions through integration. Basically, mathematically, it never blows up. And by substituting the peridynamic differential operator in local differential equations, you end up with the non-local form. And basically what you have is you have point x. It's going to be interacting with other material points within this interaction domain x prime. And so you construct the peridynamic functions as shown here, which I will show you in later slides. And the point x is not symmetrically located, and the interaction domain is arbitrary in shape. So what you do is you integrate your field variable over the interaction domain after you construct the peridynamic functions, then you end up with the derivatives of order that you want. And you construct the peridynamic functions here by satisfying this orthogonality property that I will also show you in the next slide, or the next slide after. So if you want to learn more about the peridynamic differential operator, we have a book out. It came out in 2019. It has many example problems, and all of the source codes related to these example problems can be downloaded from this site. And also Professor Fei Han at Dalian University of Technology translated the book into Chinese. It's published by Science Press China. So here is the peridynamic differential operator. It's very simple. So if you have let's say, function in 2D, we basically have a Taylor series expansion. And let's say you're interested in the second order derivatives. So we truncate the series after the second order derivatives. Okay? So we multiply each term with peridynamic functions and integrate over the family or interaction domain, as shown here. The subscript 2 here indicates that the Taylor series is truncated after the second order derivative. And P1 and P2, they indicate the order of differentiation of interest. Okay? For example, here, if you're interested in the first order derivative to x1, so you're going to have G210. With respect to x2, it's going to be G201. And here you have the second derivative with respect to x1, you have G220. And the cross derivatives, you're going to have G211. So what we do is after we multiply each term with the peridynamic function, then we say, okay, if I'm interested in only the second order derivative with respect to x1, so then this is the term that I'm interested in. So the coefficient of this should be equal to 1. All the other coefficients associated with these integrals should be equal to 0, right? Then that gives me the second order derivative with respect to f by just integrating what you see on the left-hand side here. If you're interested in the cross derivative, x1 and x2, then these coefficients will be equal to 0, and this one will be equal to 1. So that way, we construct the orthogonality condition here. So here, the peridynamic functions, you can assume them to be in any form, but here we assume that they're a polynomial with some unknown coefficients. And associated with each peridynamic function, we have unknown coefficients here, A00, P1, P2, for example, 1, 0 associated with the first term, the second term, and so forth. So the degree of interaction is specified by W. We can assume it to be the same for each term here. And I'm going to assume that to be W. And if I enforce the orthogonality condition that I showed you on the previous slide, I'm going to end up with a system of algebraic equations to determine the unknown coefficients of the peridynamic functions. So this is my shape matrix A, and the unknown coefficients, each column that you have here represents the unknown coefficients of the peridynamic functions. And the right-hand side is my known values coming from the orthogonality condition. So once you solve for the system, you determine these coefficients, put them back in here, and then you go back, and then you perform your integration, you end up with the derivatives of interest. So that's very simple. And now if you assume that this domain of interaction is spherical, and if you have a point at the center of it, then you can evaluate these peridynamic functions analytically. And this is the form that you have for the grad, divergence, and del operator. Okay. So if you take these expressions and substitute them back into the Navier's displacement equilibrium equation that we have, and then what you do is the non-local form of the Navier's displacement equilibrium equation becomes this. And it's the same as what Silling derived in 2007. Okay? So we do recover the peridynamic equilibrium equation derived by Silling if you assume that your interaction domain is spherical and you have a point at the center. So peridynamic discretization, you can have discretization in space, like for two-dimensional analysis, or you can actually have it in space-time. So this differential operator also applies to time. So for example, if you have a space-time discretization, the point of interest will never have a symmetric position in the interaction domain, because whatever happens in the time direction is going to be always in the past. So it's going to be always non-symmetrically located. Whereas in the case of space discretization, so this point here may have a symmetric position within the interaction domain, and whereas near the corner, you're going to have a non-symmetric position. Periodic boundary conditions are very easy to construct. All we do is, if you have a point here, we bring the information from this corner, and basically we complete the interaction domain of this point X. So we bring information from this side, put it over here, from here, and so forth. So as I mentioned, we basically complete the horizon of the point in the corner or near the boundaries here. So we don't have any additional constraint equation to enforce the periodic boundary conditions. And the convergence is basically, we follow an approach suggested by Bekar. So you can have, we perform a delta M convergence in all of the results that I'm going to show today. So we let horizon go to 0, we let the grid size go to 0, and we make sure that we have delta M convergence taken care of. So here's an example of a peridynamic differential operator. So if you are interested in taking the derivative of a step function, we know that the local differentiation is going to give us a direct delta function. So here basically, this is my peridynamic function, and I'm truncating the Taylor series after the second order terms, and I'm interested in first order derivative. So as the horizon size goes to 0, basically I go from 6 delta x to 3 delta x. You can see here that I am recovering the behavior of a direct delta function. And this is the same as what Silling and Leeuw proved, that as the horizon size approaches 0, basically we recover the classical continuum mechanics equations. So I just want to give you a summary of what I'm going to do next. Basically, I'm going to construct the solution of various partial differential equations by using the peridynamic differential operator. So it's time dependent. And in time, we have first order implicit time integration. In space, we have the peridynamic differential operator. And depending on the order of the derivatives I have, this is my N basically represents where I truncate my Taylor series expansion, or the highest order of the differentiation I have in the differential equation. Delta is my grid size, grid spacing. It's my horizon. In all of the equations that I'm going to show you today, I'm using this Gaussian type wave function. And all the equations, I'm applying periodic boundary conditions and initial conditions here. For example, here we have the field itself. It's the 0th order derivative, the peridynamic representation. And here you have the divergence of the field variable, for example. It's associated with C5, and it's multiplied with the field variable. So you have the field itself, U, 0th order derivative, And you have the first order derivative with respect to x1, first order derivative with respect to x2, right? So my unknown here is this ut plus delta t. From the previous time step, I have ut, so I'm solving everything implicitly, okay? And in this case, my highest order derivative is 2, so I'm using a peridynamic function with a subscript 2. That means that I'm only considering terms up to the second order derivatives. So A here is the entity. Basically, that's the area of the material point that I have in my grid space that I showed you in this here. That would be the entity of that material point. So the result of this discretization, I'm going to do this at each time at each material at each point that I have in my domain. So I'm going to end up with a system of algebraic equations. It's a nonlinear partial differential equation. So I'm going to end up with nonlinear system of algebraic equations. So we have the we do like basically use Newton-Raphson method, and very simple. So the first or the initial guess, we use automatic differentiation to construct the initial guess, and it requires updating. But we don't want to do that computationally, it's not desirable. So we use Boyden's method for updating the Jacobian matrix. But this is not suitable for sparse systems because we have a sparse system of equations. Then to get around that, we have Schubert's method, and we modify it so that it becomes suitable for sparse system of equations. And once we do that, we use the direct solver from the Intel library. It's very straightforward. So the learning algorithm has two sets of data. We have the training data set. Of course, we have the testing data set. And we want to construct the candidate space that I mentioned before. So we're going to use peridynamic differential operator to construct the feature matrix, as shown here, and our functional that I showed you before. And we use Douglas-Rachford optimization to solve for alpha for different regularization parameter. Okay, so we use the training data, we construct the feature matrix, then we do optimization for each regularization parameter, we determine alpha. Then we use the training testing set. We use a testing set for that particular, with that particular alpha, right, that I have. So here you see the V from the testing data set. I have the feature matrix also from the testing data set. I'm again using peridynamic differential operator here, but alpha here is coming from the training data set. Okay? So I construct an accuracy metric. So for each lambda that I have, so for each lambda, I have a different alpha. So I construct this relationship that you have for the accuracy metric and lambda. What happens is that for different values, you have this behavior, and then all of a sudden you see a jump. And then the solution form that you have actually reduces. So this jump here indicates a change from the correct solution form to a reduced form. So basically your acceptable interval for lambda is here. If you want to choose minimum error, then you should get the smallest possible lambda that you have. So this is the way you identify the regularization parameter lambda. So coefficient alpha corresponding to the smallest acceptable lambda identifies the partial differential equation. So in this case, this is the one that we identify. So in all of the problems that I'm going to show today, I use that particular approach, okay? So we have the testing data, we have the training data, we have the testing data, we set the functional, then we go ahead and we determine the parsimony interval for the possible or acceptable lambdas, and we pick the smallest value so that we get the most accurate solution. So these are the equations that we looked at. To mimic a realistic measurement, so what we do is we first construct the synthetic data. We solve the field equation by using the ground truth coefficients. And then we add random Gaussian noise, and that becomes our training data and testing data. So that's really the approach that we're doing here. So the first one we considered is viscous Burger's equation. So as you can see here, I have coefficient 1, I have epsilon 0.1 here, and periodic boundary conditions is my initial condition. So I discretize the given equation, as I mentioned before. I'm going to solve it implicitly. This is my peridynamic discretization. Highest order derivative is 2, so my peridynamic function is G2. So I have the function itself, or the field variable itself, the first derivative G21, and you have the second derivative G22. And then in this particular case, it's one-dimensional. I have 401 points, and my grid spacing, horizon size, and time step. So this is the ground truth solution that we obtained by using the approach that I mentioned. And here's basically the terms that I have in my feature matrix. So these are the ones that I included, and I added 5%, 20%, or 50% noise. And for each of these, so I construct the parsimony interval, as I mentioned. I determine lambdas for different types of, for different coefficient vectors, and then put them back into the testing. And then I determine this relationship, the accuracy metric versus lambda. So you can see here, you see a jump, and then basically the form of the partial differential equation it reduces. It becomes, so we lose the second order derivatives, okay, if you go beyond that. So this is the acceptable range. And if you pick the smallest value, then you can construct the solutions. So in this particular case, we have 300 data points for training, 300 for testing. And you can see here that if you compare, even with 50% noise, we recover the coefficient very close to 1. And here, in this case, it's 0.123 instead of 0.1. But for the others, it's pretty close. And here I compare the ground truth coefficient solution with the ground truth coefficients and solution with the recovered coefficients when you have 50% noise. And this is the relative error. It's in the order of like 10 to the minus 5. Second equation is Implicit-Burger's equation. So it's a little bit more challenging. And here we have the coefficient 1. It's exactly the same as what I described before. We construct the ground truth coefficient solution with the ground truth coefficients here, and these are the terms that you have in your feature matrix. And as you can see here, you very successfully capture the unknown coefficient here for even with 50% noise. And what I have here is, again, I'm showing you the relative error between the ground truth solution with the ground truth coefficients and the recovered coefficients with 50% noise. Again, it's in the order of like 10 to the minus 4 at time step of 0.72. So then we move on to a little bit more difficult field equation. This is, it has high order derivatives, and it has randomly specified initial conditions, periodic boundary conditions, and this solution, this particular field equation was also considered by others, 2013. So we basically duplicated their work. And the discretization is the same as before. And here I have fourth order derivatives. So I decided to truncate my Taylor series after the fifth order derivative. And my horizon size is 6 times the grid spacing. And I have 101 by 101 grid spacing. The grid spacing is 0.09 meter. And that's my peridynamic solution with these coefficients that we have here. And beta is equal to 0, and alpha is 0.3, and these coefficients are seen here, 1 and 2. So here we construct the parsimony interval by using the training data set of 200 points, testing data 200 points. And as you can see here, after this jump here, the form of the partial differential equation is different, reduces. And these are the terms that we considered in the feature matrix, and it successfully captures the coefficients. So for example, for even with 50% noise, you get all of these coefficients rather accurately. Okay. for example, the U square that you have here is 0 as expected. And here I'm showing you the relative error. Again, the accuracy is 10 to the minus 3 or 10 to the minus 4, depending on where you're at. But overall, it's 10 to the minus 3, so it's fairly good. Then we have the KDD equation. This was also considered by others in the past. We have the solution available for this. So here you have mu as 0.01. Periodic boundary conditions, discretization is exactly the same as before. My highest order derivative is 3, so I truncate my Taylor series after the third order derivatives, so my peridynamic functions. My horizon is 4 delta, grid spacing is 0.02. So for all of these problems that I'm showing you, we did a convergence study. And as you can see here, the parsimony interval gives me the acceptable range for lambda regularization parameter. So it's not a tuning parameter. So we determine exactly what it should be, and we pick the smallest value to achieve the smallest error. Okay. In this case, we have 400 points in the training data and 400 in the testing. And we have mu being 101. That's the coefficient of the third order derivative. So you can successfully we capture that. And also the coefficient of the product of u and ux, we capture to be almost 1. So in this case, we have 5% and 10% noise in the data. And here you see the relative error. Again, it's in the order of 10 to the minus 4. It's very good. Then we move on to a difficult equation, Kuramoto-Sivashinsky. We were able to solve this. So periodic boundary conditions, ground truth solution, procedure is exactly the same. I want to point out I have fourth order derivative with respect to x. And so my, of course, horizon is going to be 5 times the grid spacing. And this was considered by Raisi and Cahn-Hilliard. So this is, we basically applied, we wanted to apply our approach to the problem that they considered. They used PIN. And in our feature matrix, we have, these are the terms that we considered, okay? It's quite extensive. So constructed the parsimony interval, we picked the smallest value for lambda, and we used 80 points for training and for testing. As you can see here, even with 50% noise, we're able to capture the coefficients very close to what we have in the actual equation. And here is the relative error. So this is the solution with 50% noise, ground truth coefficients, and relative error. All right, now then we'll look at nonlinear Schrodinger's equation. So this is a little bit more involved because, so again, we have periodic boundary conditions. So we split this equation into its real part and the imaginary part. So we have a system of equations now coupled. So the real part and so u is the real part and this is the imaginary part. So we end up with these two coupled equations for the real and the imaginary part of H, that's the unknown field. And discretization, everything else is the same as what I described before, nothing. And this equation was also considered by Raisi and his colleagues 2019. So they used the spectral method to get the derivatives. And we compared our solution against their solution, so they're very close to each other. And parsimony interval for the real part, and we use 500 points for training, 500 for testing. And as you can see here, even with 20% noise, we were able to capture the coefficients. It's pretty close to 0.5, pretty close to -1. So that's for the real part, and for the imaginary part. So we have again the parsimony interval feature matrix. So we have, as you can see here, different combinations. So it's a pretty extensive feature matrix that we constructed. And here I have the.
Sorry, 1 minute, please.
Yeah. Say it again.
1 minute, please. 1 minute.
Okay, and then the relative error is I can show you. So this is where we construct the constructed solution is here. It's with the discovered solution, and here's the actual equation that we begin with, and you have 20% noise, and this is the relative error. It's in the order of 10 to the minus 4, 10 to the minus 5. And the last equation I have is the Cahn-Hilliard equation. Here I have a fourth order derivative. Periodic boundary conditions, you have initial conditions random, so you have discontinuities in this field. And I'm not going to go through and describe what we're doing here. It's exactly the same as what we described here. Because I have a fourth order derivative, I'm using my horizon to be 5 delta. This is the solution we have with the ground truth coefficients. And the parsimony interval is given here. And I have 50% noise, 20% noise. And even with 50% noise, I very successfully capture the coefficients here. It's like minus 0.5, it's pretty close to that, minus 1. So, and the relative error that you see here is, again, 10 to the minus 4. It's in the order of 10 to the minus 4. Okay, so basically what I'm showing you here is that is a pretty robust approach. If you augment your sparse linear regression algorithm with peridynamic differential operator, so it's a very robust approach for discovering partial differential equations of a given time series, even with significant noise. And we split the data into a training set and the testing set to come up with the parsimony interval so that we have the correct value of the regularization parameter. And so that the transition in the relationship between the accuracy metric and regularization parameter basically is in the form of a jump. So you have a reduction in the order of the partial differential equations you have. And the peridynamic functions can be readily constructed and incorporated into any existing regression algorithm. It doesn't have to be Douglas-Rachford. So with that, I'll stop.